Good morning. We got a differential geometry problem of the day posted on 8/12. I'm trying out some different formats here. Uh, I started out doing the problem one day and the solution the next day, but I'm working on like four problems at once, and I get confused. So it's easier for me to do the problem and solution on the same day. If you have a preference, please let me know. Okay, we're going to look at change of coordinates using differential the forms. Now, in tensor calculus, we did a whole bunch of this. So let's see how they do it in differential geometry. Okay, we have a function f of x, y, and z. We want to change that to cylindrical coordinates r, theta, and z. Okay, given the transpose equations, this is the transpose equations from Cartesian coordinates to cylindrical coordinates. Find the exterior derivatives, dx dy dz. Okay, here comes the solution. Taking the exterior derivative by zero form, these are zero forms, yes, equals a one form. So we know how to do that. We just get partial fx dx, partial fy dy, partial fz dz. So we just want to plug in what our function is. And the first one is r cosine theta. So we take these partial derivatives and we get that. Then we do it with y and we get that. And we do it with z, and that's just z dz, right? Okay, part B, given a one form, this is a one form, convert this one form into cylindrical coordinates. Okay, here's a hint. First, find this part of the function, the one form, using the above transpose equations. Okay, here comes the solution. Okay, we have our transpose equations. We have our the exterior derivative of those to make these one forms. And here is the one form we want to work on, right? So we have that. We have all this. All right. And we can see that x squared plus y squared is just equal to r squared. So that makes this a lot easier. So let's put all of that in here, right? So here is x squared plus y squared. Here is dx. Z is just z. dy is this. And dz is dz. Okay, so we simplify that and we get this. All right, now let's do something with it. Find a spiral around the cylinder by integrating our one form. And what are we talking about here? Okay, here's a cylinder, and a spiral around that, as you know, is a helix, right? So we want to integrate that from 0 to 2 pi. We want to integrate this helix, the spiral, from 0 to 2 pi. Okay? So we want an integral of omega, this guy. And here's what we got. Let's let r equal 1. We'll parameterize theta and z with just t, and t is going to go from 0 to 2 pi. Okay, I said hint. Use the chain rule to find dr d theta dz. Okay, here's the solution. Here's the chain rule. So dr dt is just the derivative of 1 is 0. D theta dt dt, that's just dt. That's just dt. Okay, and so now here is our one form. And now we're going to put in everything we just found. Okay, so we let r equal 1, and theta becomes t, z becomes t, theta becomes t, but dr was 0. So that wipes out this whole term. Okay, z becomes t, r was 1, cosine t minus 1 cubed, sine t, d theta became dt, and dz became dt, So we simplify that. That's gone. That's all we got left. Okay. Now we want to integrate that from 0 to 2 pi. Now, I kept making mistakes with positives and negatives, so I had to break this up and say integral of this is A, this is B, and this is C because of this thing, which I integrated by parts, right? So integral of u dv equals uv minus integral of v du. We let u equal t, dv equals this. Oh, sorry, a cat jumped up here and spilled my drink. I had to stop and cut out all the bad words I said. Where was I? Okay. So du is dt and v is equal to the integral of cosine t dt, which is just sine t. So all right, so let's put it all back together. All right, so here is uv, and now we want the integral of v dt. So here's the first part. This becomes a negative cosine, and you got the negative there, and that becomes a positive. This is where I kept messing up. All right, so that's a, and b is equals negative cosine. That's easy. D is just t. So we put it back together, and this negative makes this a positive. So we've got 2 cosine t plus t. Okay? Now at t equal 2 pi, we got 2 pi sine t. This is 0. That's a 1. So it's just 2 plus 2 pi. At t equals 0, we got this becomes 0. This just becomes 2, and that becomes 0. And so we subtract those as you do in an integral, and you get 2 pi. So that's the answer, which actually, if you look at it, it's kind of obvious that it's 2 pi, but it was worth doing anyway. Okay? Part D, given a two form, dx wedge dy, find the area form of a plane passing through a cylinder, right? So we want to just look at this plane that passes through the cylinder. What is the equation for that in differential forms? Okay. Comes a solution. All right, so here is our dx and dy. That's all we want, right? Because z is a constant. We just want a plane. All right, so we just wedge those two together because we found dx and we found dy already. We wedge those together, and we get, we simplify, and we get this. Dx wedge dy, the plane is just r dr wedge d theta. Now, how does that compare with what we already know how to do? From tensor calculus, we found an expression for the area element, right? It looked like this. dA equals the square root of g, the square root of the determinant of the metric tensor, dI, dxi, dxj. Okay? So our coordinates are r, theta, z, and since we're in a plane, it's just r and theta because z is a constant, right? So dxi dxj just becomes dr d theta. And what is the metric tensor in Cartesian, in cylindrical coordinates? GRR is 1, g theta theta is r squared, gzz is equal to 1. What's the determinant of that? It's r squared. What's the square root of that? Just r. So they look very similar. Okay? Last one. Given the three form dx wedge dy wedge dz, find the volume form in cylindrical coordinates. Okay? Solution. You already did dx wedge dy, so you just wedge it with dc. It's that easy. Okay? That's all there is. And from tensor the calculus, it would be the equivalent. All right. That's it. I'll see you next time.